Hi, I'm Reyne from the University of Sydney, and I'll be going through practice problem sample J. Now, as with the previous ones, I've kind of looked at this by first considering the tests. So here we can see at the top, we've got our 3 tests here. Testing for unsaturation using bromine water, we see no color change. So let's cross that one off. Tells us that there's no double bond or single bond present. When we think about the oxidation test, we're using acidified potassium dichromate. We're looking for alcohols or looking for ketones. And here we see the solution turns green. So that must mean that there must be an alcohol or an aldehyde. Sorry, I said ketone earlier, but I mean aldehyde. We can't oxidize ketone, unfortunately. Finally, carboxylic acid test, we're using sodium carbonate, and we see no bubbles, so there's no carboxylic acid present. Now, we'll come back to these towards the end to kind of confirm what we think. And as I've said before, I tend to not look at the IR or the mass spec to begin with. I leave those and I come back to those as kind of like a confirmatory sort of stage. So if we jump down here to our carbon and proton NMR, we can start to pull apart a bit of the information. So first of all, carbon NMR, we can see 1 peak and 2 peak. And there's a couple of things to pull apart here. First of all, we can see that our number 1 peak is downfield. Its chemical shift is headed down towards a higher ppm. If we recall, that relates to the idea that that carbon environment must be next to something that is de-shielding it, pulling electron density away from it. For instance, an alcohol or an aldehyde. Okay, so this is putting together some pieces. It's making sense. Now the second peak is much lower, meaning that it is not being affected by something that's pulling electron density away from it, or at least much less so. Its shift is about at the 25 area. There's another piece of information that we can pull from this, and that is the heights of these peaks. So if we compare the heights of these peaks, our peak number 2 looks to be roughly twice as high. Now, when we talk about the proton NMR, it's all about integrating the area underneath peaks. Carbons tend to be a lot sharper, so we can kind of relate height a bit more easily. But that's telling us that there's likely going to be twice as many carbon environments at peak 2 than there are at peak 1. Now, that doesn't mean that there are only 3 carbons. That means that there could be, for instance, 6 carbons. So 2 carbons at peak 1 and then 4 carbons at peak 2. This just tells us the ratio, and we'll come back to that a bit later as well. Now, the proton NMR, we can pull apart some information here as well. There are 3 peaks present. Now we can see this peak, a singlet, at about, what's that, about 4.8, okay? And that's a singlet. We can then also see, if we zoom in here, right? And you can see that they've zoomed into this with that kind of aspect to show you how many peaks this has, right? So for 4, at about signal 4, we've got our signal B, I'm calling it, and it's got actually 7 peaks. Is there 7 there? There's 7 there, all right? Now, this is what we would call a septet, and we'll come back to that in a little bit, but that's worth noting. And then finally, we see peak C over here, and that's going to be a doublet. All right, so 2 peaks beside one another. Now we can pull out a bunch of information from this. So let's first think about our chemical shift. Chemical shift, as it goes to a higher ppm value, it's downshifted, has the same idea that it's being de-shielded. Now, this tells us that whatever is down at about the 4 and 5 area must be closer to something that's pulling electron density away. Now, the singlet, we are already thinking about the fact that there is possibly an alcohol or an aldehyde. And often when we see a singlet around that 5-ish area, it can move about. That is a bit of evidence that points towards, for instance, an alcohol. So the proton in an alcohol can often be that singlet. The reason that it's a singlet, it doesn't tend to interact with the protons in the carbon-hydrogen environments that are around it. The peak at 4, though, is very distinct. It's downshifted down, right? And that's telling us that it's likely going to be adjacent to that oxygen, whether it's an alcohol or a carbonyl, or alcohol or an aldehyde. We aren't certain just yet, but it has been shifted down. Now, finally, the peak C is much closer to 1, which is telling us that it's not close to that alcohol or to that aldehyde. So it's got a little bit of distance away from it. And we can kind of confirm this as well when we come down to look at the peak data table below, where we can see that the peak up at 4.8, the one that we think or suspect may be an alcohol, there's only 1 proton that's there based on the ratio. And similarly, when we look at the peak B, where we see that septet, it's saying that there's only 1 proton there. Now, if we think about how many bonds that a carbon can form, that's telling us a little bit of information about the sort of structure we might be thinking about. Maybe this alcohol or an aldehyde, but likely an alcohol, more evidence is coming towards it, is something that is a bridging carbon, and it's got 1 hydrogen off of it already. Finally, we see that there are 6 hydrogens at peak C. Now, we can't have 6 hydrogens on the 1 carbon. Now, so this is suggesting that maybe we have more than 1 carbon that is having the same proton environment. So we're thinking now, perhaps it's 2 terminal carbons, or maybe there are 2 bridging carbons that happen to be quite similar to one another. Pieces are starting to come together. Let's move back up here then to think about our IR and our mass spec. So we'll start with our mass spec. The molecular ion mass is 60. And as I've said before, let's start with the simplest case, right? So we've already said here that there is 1 carbon environment at about 65-ish for our carbon NMR. And then there is another peak at about 25, but it's twice as high. So let's assume that there is 1 carbon and 2 carbons in that process. So we have a total of 3 carbons, which would give us 36 towards that molecular ion. Now, we've already checked up in that test up here that there is an alcohol or an aldehyde present. Something has been oxidized and there's no double bonds or triple bonds. So this then tells us that we must have at least 1 oxygen, which would give us 16. We add those up together, we've got 40, 52, 52. And now we need to think about, well, how many hydrogens are there present? And if we come down to our peak data table, we sum those 3 together. Once again, we're assuming the simplest ratio is what's correct here. There are 8 hydrogens present. So let's try with 8 hydrogens. This gives us 8, and that sums up to 60 on the dot. Pretty good sign. So that's telling us that we do in fact have 3 carbons, 1 oxygen, and 8 hydrogens. So really the last thing we need to piece together before we start suggesting a structure is now thinking about, can we confirm whether this is an alcohol or an aldehyde? And that's where the IR comes in. IR is very powerful for telling us if particular functional groups are present. We can see our normal carbon hydrogen stretch here at about 3000. We can see some carbon hydrogens bend at about the 1450 area. We can see there's a fair bit going on in the fingerprint region, but that's always kind of hard to interpret. And often it's the carbon-carbon bonds that's involved there. But we then have this 1 peak up at about the, what's that, 33 to 3500 sort of region. And if we consult the table that's earlier in this document, you'll find that that is an OH, okay? And I mentioned it before in another example, but the broadness of that peak is to do with hydrogen bonding. It means that there are many variations on the kinds of stretches that can occur for that OH when it's being measured. So rather than a very single sharp peak, we see a nice broad peak. Alternatively, if we were looking for, say, an aldehyde or a ketone, so carbon double bond oxygen, otherwise known as a carbonyl, we would expect to see a very sharp peak at about 1700, and that is not present at all. So that confirms for us it must be an alcohol and not an aldehyde. So based off of this information, let's come down here and think a bit. We know that we have 3 carbons. We know that we have an alcohol. And the really key thing here, right, change to purple, is this 6. This is what really stands out for me, because this tells me that we likely have a symmetrical molecule. It tells me that in this case, the 2 terminal carbons must be the same environment. So if we think about what that would look like, we propose something like this. So propan 2-ol. Let's start labeling our different pieces. If we think about our carbon environments, well, the carbon that is closest to our oxygen and therefore de-shielded most must be that central carbon there. It's right next to the alcohol. We then think, well, we only have carbon environment 2. We put that there. But if I just pick maybe green, right? Don't forget, we have a certain symmetry here, which means that anything on the left-hand side of that dotted green line will mirror on the other side. So this means that we can also assume that that carbon is also the carbon environment at peak 2. It matches the ratio of those heights we looked at. Now, finally, switch over to red. Let's think about matching our proton environments. Now that singlet, peak A, is likely, or is, that proton off of the alcohol. It doesn't interact, it doesn't split with any adjacent proton environments. When we think about which proton environment is going to be most de-shielded, it's peak B, which would tell us that it's going to be this one there in the central carbon. And in fact, there's only 1 proton there. There's only 1 proton possible, because if you think about the carbon, it can only have 4 bonds. There's a carbon oxygen, 2 carbon carbons, and there's only 1 carbon hydrogen possible. Finally, that leaves us then with peak C, which must be the 2 terminals. Again, they are mirrored. We have that symmetry. And that's it. So we would call this propan 2-ol. Cheers.